it. All right, and now let's do a search. You're going to go for all your classes and you're going to find your final exam schedule. It's going to be for all the exams. We're going to go to this website here and do this search, and you go find it. So let me know. It's very important. So if there's any conflict, I hope it's not. So there's the class. It should not happen. So we need to know it. So here it's this is for no, this one here, the exam. Okay, for 2023 final exam schedule. Okay. So now we're gonna look for this, the full term. Yes, this is the full term, and look for the Monday, Wednesday, Friday. All right, so this one right here. You see this now here? This one right here? It's our time. It's going to be on Wednesday, December 6th from 10 to 12. So this is the final exam time. Okay. All right. I'm going to put this final exam time and on the announcement so that we're going to keep the final exam here. I'm going to copy and paste this. So put this in the announcement here. Okay. I'm going to see if I can put this in announcement somewhere. Okay. And let's put this. I'm going to put the in-folio announcement for this final exam time. So here, I'm going to have this final exam. So the final exam time and the final exam is comprehensive. Okay. So we have more time. We have 2 hours. So you can expect the amount of the material is about the double of the regular exam you have in the past, exam 1, exam 2. All right, and the format will be the same. You're going to submit to folio, and you can write a program and the multiple choice. All right, let's go back. I'm going to go save this so then you can have this. How do I save it? Let's see. Okay, publish and save. All right, now let's go back to chapter 28. So I'm going to go back to chapter 28. And this is all right, this is chapter 28. So I'm going to open the book. So please note that we will not have class on Friday. I'm going to post a video to give you hints on programming projects in chapter 28. So let's continue now in chapter 28. We finished depth first search last time. So you see the process of the total thing here is design. You design your object-oriented system, and you have identified all this the objects and all this. For the objects, you have the classes to model the objects, and you identify the relationship among all this classes, and now you get into implement all these methods. So a lot of time, and the methods are straightforward to implement, but for data structures, we have the algorithms. So like this depth first search. So it is not really simple matter, and we need to look at design and see what is the algorithm. And from the algorithm, so here's intuition, and then from the intuition, and we get to describe the algorithm, and then we have to implement the algorithm. All right, so that's depth first search. All right, with depth first search, there's a lot of applications. Many of these applications. So here's another application. It's interesting application here. I'm going to show you here. This is the one here. The one is we write this GUI program here. Let me see if I can. I can give you a quick demo here how this works. All right, so let's see if I can get to this and try this. Okay, yes, all right, I'm going to share the entire screen first now. So let's do this now. It's connected to SoCos here. It's this is the code here. Let's do this first. I'm gonna get Java connected SoCos.java. Okay, this one. All right, let's share this. Maybe it just shares this screen now. I'm stop sharing and I'll reshare the screen now. This share just to focus on this one screen. All right, you see this one here. This is my Java program here. I use the mouse. You can create a circle. So let's create another circle. Let's create another circle here. All right. So this circle is now not connected. But if you add this one here, and you add one here, and then you see everything is connected. Now everything connected, you're gonna have one color for all this. It's all red. Now if you add another one here, it's not connected anymore, but you add one more here, everything's connected. So here, and how do you write this code? All right. Okay, so there's several parts here in this program. Is the simple thing is, how do you draw all those things? And this is if you
Java
just get
FX.
some, yeah, right.
Or any other GUI library.
Yes, right. If you get some experience, so that part is easy. Okay, in any programming language you can do it, but the difficult part is how do you know all this is connected? Okay, so when you do a lot of game programming, there's something motion, some certain events. How do you detect it? So that's algorithm. So how do you do this for this one? So what we're doing actually is each circle is going to be modeled in a graph as a vertex. So if two circles overlap and there's an edge between those two vertices in the graph, that becomes a graph problem. You just now reduce the problem to see if the graph is connected. If it's connected, and then you just give the red color for every circle. So that is the problem. Okay, so I'm gonna go back now to reshare the screen to this one now. All right, so you see my back to the book now. So this is the screenshots here. You just saw it. and that's right here. All right, so that's the one, and so please then study and read it and see how this works. And now I'm going to move on to the next, is to introduce the breadth first search. Breadth first search. So in the depth first search, you go starting from any vertex, you go search as far as you can, and then if you don't have anything to go, and then go backtrack and then further from that backtracked point down. So for the breadth first search is you start from any vertex, and you visit this one, and then you're going to visit all its neighbors, and then neighbors. Okay. So if you have any questions, just speak to me, because that's really most effective, because I don't, just go back to check the chat. Okay. So if you need my answer, so please speak to me directly. Okay. All right. So let's see how we do this breadth first search. And now first, let's look at the diagram here. This is the diagram. Here is the graph. And we're going to start from any vertex. Let's pick 0. All right. So here's 0 and this is 0. And now all the neighbors, not in any particular order. So this is 1, 2, 3, just for convenience. So this is 1, 2, 3. And then all this. And then the last one is 4. The neighbors of neighbors here. So the level by level. So the result is a tree. So this is called a breadth first search tree. So the root is the starting point. Okay. All right. So how do you describe it? How do you describe it? This, you're going to do the search. All right. So you describe it and to write it the algorithm. And so this is the algorithm here. I'm going to do it is this is for the breadth first search starting from vertex V. So this is for the graph we have. So it's vertices and edges. And so the output is a breadth first search tree. So this tree is a search tree right here, the search tree, right? Search tree. Okay. Okay. So what we do here is we're going to now how are you going to do search, maintain this order, the neighbors. So what we do is we're going to use a queue. So initially it's empty queue. So initially this is empty queue. So we're going to have this queue is for storing the vertices to be visited. They're going to be visited, but it's in this waiting queue, wait to be visited. All right, the first one is the V. We're going to put this V into the queue. So V is going to be the first one in the queue, right? Now we're going to mark V is visited. So V is now visited. So we're going to look at all the queue. I think we can slightly modify this algorithm. So here is this. So this is yeah, we can put this mark V visited here now. Why the queue is not empty? The queue is not empty. So now the queue is the V is inside, so it's not empty, right? DQ a vertex. So the first one is V, and say this one you DQ'd, it's say U. So U is the one out, representing the one you just DQ'd from the queue. Add U into a list of traversed. So it's already been traversed. So in the queue is waiting to be traversed, and this list is in this order it's traversed. All right, into this list. For each neighbor W of U, if W has not been visited. Now, if this W has not been visited, add W into the queue. Set U as the parent for W in the tree, in the search tree. So eventually the search tree right here. All right, mark W visited. So every time you put something, I think into, so this W is now mark W visited. Let's say for each W, yes. So you put add W into the queue, so the mark W is visited. All right, so you're not going to re-put this W into the queue anymore because it is now marked as visited. Okay. All right, so this is the algorithm. All right, so now you see this is the algorithm. It's very close to the real code you're going to implement. So this algorithm is language independent. It's not particularly Java or Python or anything, so specific language, but it just describes things you are going to do. It's very close to your eventual implementation. All right, so now we're gonna see how we're gonna implement it. So it's really interesting. You're gonna see this here. This is the algorithm, and see how an algorithm match to the implementation. So the implementation. So we're gonna implement it now. So I'm gonna copy and paste this tab. So we have this. I'm gonna show you with this here. You're gonna see this, how close this implementation is. Okay, back here now, 28. So this is the code. Okay, so the code here, look at the code here, is this one here, the breadth first search. Okay, so the breadth first search right here. Okay. All right, breadth first search right here. Oh. Okay, so okay, right here, breadth first search, breadth first search. So breadth first search. Eventually, this is what we're gonna get. We're gonna return. So just make sure that is going to, you're gonna return a new search tree, something you're gonna write it here. Okay, it's going to be return this a search tree. Okay. Now what you need in the search tree, so look at the constructor. You have the root, the parent, and the search order. So it's going to be like this: root, parent, and search order. Okay, now what is the root? Root is going to be V. So V is going to be your root, V. So, sorry, it's just all right. It's this. It's V. Okay, and the parent is here. We have this parent here. So when you go to this breadth first search, so you have this vertex, all its neighbors searched. They are the children of this one. So the parent is for each one you search, the parent is the one. It's right here, the parent. That's the information, and it's a parent. Okay, initially, so look all this parent, this -1, indicating that they don't have a parent now determined yet. So this is the this one. All right, this is search order as a list. Okay, so here's the queue. So we are using a queue data structure in this implementation. We're using the queue. It's going to be first in, first out, right? So this is the queue. In Java, we can just use linked list. And Java does not have this queue data structure. So let's just use linked list for data structure for this queue. And is visited, so boolean. Okay. All right, now we're going to add this v into the queue using this method offer here. So offer this and into the queue, and this v is now is true, is visited. So if you come back to look at this algorithm, it's right here, this part here, and you add v into the queue and the mark v visited. Okay. All right, so here why queue is not empty, so you get a u. So this is dq and pull one element from the queue. So this is dqu and add u to the search order. So here is exactly here now, dq a vertex say u from the queue, add u into a list of traversed vertices. All right, so now I'm back here is look at this for the neighbor, each neighbor of u. So you get this edge right here. So this is the edge neighbors, you get all this edge. So for this edge E has uv. So this is u is actually this u, and so here eu is u, and here and v e dot v. So let's call e dot v is w. So this one is w here. W each neighbor w of u. All right. If w has not been visited, is not visited, you're gonna now add w into the queue and set w's parent to u. And is visited, w now is true, w is put into the queue. So look at this and do this, all this search. Eventually you get this v, get the parent, and get the search order. So this is return as search tree. So look how you implement it. Okay. And the time complexity, it's all of the cardinality of v and plus the cardinality of e. So it's actually, it goes with the number of edges. It's more than the number of vertices. So this is the time complexity. It's all of see the time complexity for this. It's all of this is the notation, cardinality of E plus cardinality of V. So cardinality means the number of edges, the number of vertices. Okay. So but E should be the one, the dominating one. So you can just go with all of E. Okay. So now let's go to look at, so this is the test code. So you create a graph and apply the breadth first search. So for this, so this is the result of the breadth first search. And here's the application. So there's a very similar application to depth first search, but there's one is very interesting for this is to find the shortest path. So look here, Chicago. I want to find the shortest path from Chicago to Miami. So there's many passes you can go to Miami. What is shortest path? Is to use the breadth first search tree starting from Chicago, and you're gonna find in the search tree. So you find the path from Miami and to Chicago. So that path is the shortest path. So this is 1, 2, 3. So like if you have this is as a flight map. It's a minimum number of stopovers, and so that is going to be Chicago Kansas City, Atlanta, Miami. So like this. So this is the using the breadth first search. Okay, this I'm gonna do this next time. Give you some time to go through all the materials. Is this the interesting tails problem? So let me first describe the problem. This is the problem: is you have 9 coins, has 2 sides and head and tail. So this is H is head, and this is tail. So it's in this. Put this together in this 3x3 grid. This is the random. They go on the head and tail. So the objective is to turn everything into tail. Okay. If this is already tail, you cannot change it. So this cannot be changed. Cannot flip a tail. All right, you can only flip a head. So when you flip a head, you're gonna flip all its neighboring elements. So you flip this one here, H, okay? All right, you flip this, you're gonna flip this H and this H, and this 3H is becoming T, and this T becoming H. All right. So the objective is to have the minimum number of flips. So this is one flip. Okay, everything now. See here, this is T. And there's one more flip, it's right here. If you do this one more flip, and then everything becoming T. All right, how do you do this? Using minimal number of flips. So it's, how are you gonna solve this problem? We're gonna solve this problem by reducing it and into a graph problem. So we use a graph to model this, all this, and then we use applied breadth first search for this. So it's very interesting. So I'm going to let you have a chance to look into this, and then we're going to talk about when we come back next week on Monday. Okay, all right, any questions? Questions?
No, I'm good.
Okay, thank you very much. Have a good week, and so we're gonna see you on
Okay,
Monday.
bye. Thank you.
Bye.
Thank you, sir.
Thanks.
Have a good one.
You too.
So when did you say there was not going to be a class?
Just a second. Let me just stop recording, and just a second. Let's do this. It's still being recorded. Let's do this. Turn off record.